Hi everyone, this is Mr. Zikri. In this episode, we're going to study about moment of inertia. By definition, moment of inertia is the resistance of an object to change in rotational motion. The harder the object to rotate, that means the bigger the moment of inertia. The easier an object being rotated, that means the smaller moment of inertia. I'm going to ask you to follow my thought experiment here. For example, I have two beam or rod, and then both of rod I put a weight at the end of the rod. The first rod, the mass of the weight is small m, while the other one has big M. Both of the rod is to rotate like this. Which one is harder to rotate? The light one or the heavier one? Yes, the answer is 2. That means moment of inertia of an object depends on the mass. Right. Now, here I have second thought experiment. First rod, second rod. Both of them has the same length and the same mass. And then I add some weight that also has the same mass. This is the first one, this is second one, but at the second beam, second rod, the mass or the weight is put closer to the center of rotation. The question stays the same. If you are being asked to rotate first and second object, which one is harder to rotate? Yeah, the answer is number 1. Why? Because it has bigger distance to the mass. Bigger distance to the mass. While the second one, it's easier to rotate this one. So moment of inertia depends not only with the mass of the object, but it is also depending on the distance to the rotational axis. But it's not only the radius, it's actually r squared. So we can write down that if we have an object that is rotating around the rotational axis like this, or m, so moment of inertia of the object is m times r squared. Mister, there is a question. What if the mass is not only this one but several masses? So moment of inertia of the object, then the system, is the sum or total of moment of inertia of each mass. So if we want to write it down, I equal to m1 r1 squared added by m2 r2 squared added by m3 rt squared. What if there is still more? So if there is n number of mass, we can write down mn times rn squared. If there is 1,000 mass, you have to write all the mass multiplied by the distance squared. In math, in statistics, we can write it down easily. If there is 1,000 or n number of mass, we can use sigma from S, from Latin letter S, sum. So we can write mi ri squared. I is index. I starting from 1 until n. For example, n 100. So this is simple way to write down moment of inertia. What if the object is regular in shape? Ring has mass that is have same distance to the center. So we can write down that the moment of inertia of the ring is mass times r squared. The disk. If we want to calculate the moment of inertia of the disk, remember that this disk consists of small particle that has mass. Let's say m1, m2, and so on, and it has a certain distance to the radius, to the center, r1, r2, and so on. So by calculating each molecules in this cylinder or disk, we have that moment of inertia is a half mr squared, while for the sphere 2/5 mr squared. For this very small object, very small particle, instead of using sigma, we can use integral. So the definition of inertia becomes integral x part of the mass that is calculated from center of the object to the radius. From this equation we can get here. We can get this formula easily. Example: calculate the moment of inertia of two objects that are fixed on a road. A from the middle point. So there are two objects, mass 1 and mass 2, and having distance r1 and r2 to the center of rotation. So it is rotated this point. So let's answer the first question. Moment of inertia is mass 1 times r1 squared added by mass 2 times r2 squared equal to 5 times 2 squared added by 7 times 2 squared. We have 20 added by 28 equal 48. The unit of mass is kilogram and the unit of distance is meter squared here. For question point B, the mass 1 still the same and the distance r1 is this one, 0.5. Mass 2 7 kilogram and the distance is 4.5. Let's calculate m1 r1 squared added by m2 r2 squared. m1, 5 times 0.5 squared added by 7 times 4.5 squared. 1.25 added by 141.75. The answer is 143 kilogram meter squared. Next, here we have several rotational quantity that is similar with linear quantity but are not the same at all. In linear we have displacement, in rotational we have theta angular displacement. In linear we have velocity, in rotational we have omega angular velocity. In linear we have acceleration, in rotational we have angular acceleration. In linear we have mass, in rotational we have moment of inertia. In linear we have force, in rotational we have torque. In linear we also have kinetic energy, which is half times mass times velocity squared. So this mass is substituted by I in rotational motion and V substituted by omega. So we have rotational kinetic energy as half moment of inertia times angular velocity squared. We have in linear momentum P equal to mass times velocity. In rotational motion we have L, angular momentum, equal to moment of inertia times omega. In linear we have work, force times displacement, F here substitute by torque in rotational, and X here substitute by tau. So work in rotational motion equal to tau torque times theta angular displacement. And the last one, you know that force equal to mass times acceleration in linear motion. It will be substitute in rotational motion as tau equal to moment of inertia times acceleration, angular acceleration. Here is a picture of a tire that is rotating at its center, but it's not moving anywhere. So this tire has only rotational kinetic energy, a half I omega squared. But here, this bicycle, instead of this bicycle, while having angular velocity, it also moving in a straight line, so it has linear velocity. So it has rotational kinetic energy and also linear kinetic energy, as presented here. Half mp squared is kinetic energy of motion in linear, and half I omega squared is kinetic energy of rotation. So if we sum this up, it becomes total kinetic energy. This total kinetic energy is being possessed by an object that is rotating and translating in the same time. Here, an example. There are three objects here. A ring, a cylinder, and a sphere are released from the same height. Which one reaches the bottom first? Find their velocities at the bottom. So here we have ring. Let's write down its moment of inertia. Moment of inertia of the ring is m r squared, while for the cylinder, moment of inertia is half m r squared. And then while for the third one, the sphere, it has 2/5 mr squared in moment of inertia. Here in the ring, actually there is 1 in front of mr. mr times 1 becomes mr, so we don't write it. So here, as you know, moment of inertia will define how hard the object to rotate. The bigger the moment of inertia, it will be harder to rotate. So from this info, we know that the smallest moment of inertia is possessed by the sphere, while the biggest one, is possessed by the ring. So from here, sphere will reaches the bottom first because it has small moment of inertia. It will reaches the bottom first. Now let's find answer of question B. Now as you can see here, moment of inertia is actually k times mr squared, while k is a number starting from 1/2, 2/5, and then 1/3, 1/12, and so on. Look at here. The object at the beginning, it has height of 8. H. So at this point, each of the object has potential energy, while they don't have kinetic because they are not moving yet. At the bottom, the object rolls, and it is also having linear velocity. So at the bottom, the object has rotational kinetic energy and kinetic energy, but they don't have potential energy because it's already at the base of the inclined plane. So by using mechanical energy conservation formula, mechanical energy at the first condition should equal to mechanical energy at the second condition. In the first condition, the object only has potential energy, while the second one, there is rotational kinetic energy and kinetic energy. Let's write down here potential energy mgh equal to half I omega squared added by a half mv squared. Now we have to convert this I and omega into linear quantity. So we know that I is k mr squared, while omega v over r. So mgh equal to half k m r squared v over r squared added by a half mv squared. So we can cancel r here, and then also we can cancel mass. So it's only left a half kv squared added by a half v squared. Let's factorize this half v. So half v squared times 1, k added by 1. Moving here, so let's multiply each side with 2. 2gh equal to v squared times k added by 1. Move this part here, so v2 equal to 2gh over 1 added by k. v equal to square root of 2gh 1 added by k. To answer for B point, you have to understand what is k1, k2 and k3. Then you can answer what is the velocity of each v1, v2 and v3. That's all for today, guys. I hope you can study from this video easily. I will post another video next time. See you guys. Bye bye.